Any general questions, problems, anything? I was going to talk about Project 3 a little at some point, but maybe I'll just send it out in an email. There's a few people. Because, of course, this thermo slash equilibrium piece is really what Project 3 is all about. Right. It is really thermo, as you will see in about 10 minutes. K is really just thermodynamics masquerading as an equilibrium constant. But again, it's one of those things depending on what subdiscipline your reaction falls into. It might be more common to talk about delta G's and H, or be more common to talk about equilibrium constants. So you kind of want to be on the lookout for both. I want to take a look at one more little sort of delta G problem before we move on to talk about equilibrium as it relates to thermodynamics. And, you know, we had talked about this earlier in terms of evaporation of water, or it could be boiling of water, right? Because I'm really just talking about a liquid to gas transition, right? And as we mentioned, this is enthalpically unfavorable, right? If you calculate the delta H for this reaction, again, at 298 Kelvin, because that's where my tables are located, I get an endothermic reaction, and endothermic is, as I like to phrase it, a thumbs down from the universe, right? On the other hand, if you calculate the entropy change for the same reaction, right, as we've talked about, gases are more entropic than liquids, and so unsurprisingly, if you calculate, again, technically the standard entropy change, since I'm using my tables, right, the entropy change is positive, which is a thumbs up from the universe, right? And so this process could be viewed as being entropically driven, right? The universe doesn't really want to do this from an energy standpoint because it's going uphill in energy. On the other hand, it does want to do it from an entropy standpoint. All right. And of course, the balance between enthalpy and entropy is my Gibbs free energy, right? And so if I calculate the Gibbs free energy for that reaction, again, at standard temperature and pressure, I get a positive 8.5 kilojoules, which is not spontaneous. Right. And I kind of sort of know that because water doesn't boil at room temperature, right? And so for the phase change, it's really spontaneity that defines the boiling point or melting point for a material, right? If I actually calculate the delta G at the known normal boiling point of water, 373 Kelvin, I get a really small number, right? I know it's 312, but it's 312 joules, right? Most of these numbers have been kilojoules, right? It's slightly negative, it's spontaneous. In fact, it really should be zero, right? Because what I really have is the equilibrium, at the boiling point. And the only reason it's even slightly non-zero is because of my problems with the data tables, right? I calculated that delta G at 373 using my data tables at 298 Kelvin, right? And as I talked about earlier, right, I don't have a lot of choice if I'm not at 298 Kelvin because I don't have data tables at every possible temperature. And so this calculation of delta G from the separate standard delta H's and delta S's is always just an approximation, which is why I get a slightly non-zero number here at the boiling point, right? And so, you know, as I said, if you use those tables, it will get you close, but they're not going to be exact if you're not at 298 Kelvin. In fact, if you use those thermodynamic tables to find the boiling point of water, right, where the delta G for the reaction is 0, right, you get 370.4. So you're off by a couple degrees, right? Right. And so, you know, there's two morals to that story, right? One is the caveat that if I'm not working at 298 Kelvin, right, I know I'm approximating. That might offend thine ears, right? If you're still under the delusion that science is pure and perfect and always exact, right? If you've embraced the dark side and recognized that science, right, strives to be exact and strives to be objective and therefore pure, but is in fact, like everything else, flawed, either in measurement or theory frequently, it's not as disturbing as it might otherwise be. Right. Right. And the other moral to that story is the phase change issue. Right. That's what really defines my phase change. Right. It's not so much that I cannot melt a little bit of ice, right, at temperatures below 0, right? It's that I haven't reached full-blown equilibrium for the reaction, which is what actually defines my phase change temperature. Questions on that? Problems? Anything? Right. And to that end, right, I maintain that it's all about thermodynamics all the time, right? Even when we were talking about equilibrium, we were just talking about thermodynamics and didn't know it. All right. The reason becomes more apparent if you think about it in terms of Q and G, right? I've talked about the fact, to Owen's point in the chat, I don't really want to get bogged down on this. The question was, why are phase changes related to equilibrium? Because that is the definition of a phase change, right? You are balancing the two phases. Otherwise, you would be melting at any temperature possible, right? That is why, unless you drive your phase change to completion by continuing to add energy to overcome the enthalpy change, you just sit there in a balance between the two phases. I mean, it doesn't have to be solid and liquid or liquid and gas, any of the two phases. It is the definition of a phase change. Now, anyway, so reaction quotient, right? Q right, as it's called. Again, we've used it most recently for KSP. You could, in theory, have used it for any equilibrium problem. We really just didn't need it, right? If I had a random equilibrium that wasn't a KSP, I always got to equilibrium. So there wasn't really any need for Q, although Q would have told me one thing that might have been useful to know, but is not necessary to know. And so, random equilibrium problem, I don't really care about the numbers. Like all equilibrium problems, 3 parts. So there it is, balanced equation, initial conditions, of course, right? There's a change line. But of course, the reaction in this case could be going either left or right, because I started with a little bit of everything, right? I've got a little bit of product and a little bit of both reactants. And so equilibrium might require me to make more products or make more reactants. It depends on where I am relative to equilibrium. And Q would tell me that, right? If I calculate the Q for my initial conditions, it's 1 in this particular case, right? I've got 0.5 molar water, 0.5 molar hydrogen, and 1 molar oxygen. If I calculate it using, again, the equilibrium expression with non-equilibrium values, Q is 1, right? By itself, that doesn't mean anything, right? But if I compare Q to K, the K for this, as I expressed it in the problem, was 1.6 times 10 to the minus 6, right? And so, as always, Q tells me where I stand relative to K. In this case, right, Q is significantly larger than K, right? And since both Q and K, since they are the same functional form, are products over reactants, what that tells me is I have too many products, or if you prefer, if you're a glass half empty kind of person, I have too few reactants, right? In either case, it doesn't really matter, because if I turn my reactants into products, I would be increasing the products and decreasing the reactants. On the other hand, if I turn my products into reactants, I would be decreasing the products and increasing the reactants. All right, and so both work in my favor depending on which way I want to go. In this case, if Q is too big, I want fewer products and more reactants, which means I need to have the reaction running to the left. All right. And frankly, I could have done that for every reaction we solved in the entire equilibrium section. There really just was never a need, all right? Because ultimately, except for KSP, where I don't necessarily ever get to equilibrium, my initial conditions just evolve, whether they're going left or right, till I get to equilibrium, and the math takes care of it for me. I don't even really need it for KSP, other than it tells me when I don't have to do anything. All right. And so as a general rule, what Q tells me is where I stand relative to K. I'm either less than K, right? Too small, that is, in which case I need more products so the reaction goes right. I'm too big, as in the example we were just looking at, in which case I need fewer products so the reaction goes left. Or if by some chance Q equals K, I'm actually already at equilibrium. And so in that sense, Q is a directional arrow for my reaction, right? I never really cared because, right, I would just get a negative X value if I just solved this the old fashioned way where it was minus, right? My general rule, because I try to keep things similar, so I don't have to think too much, right? And B, every problem gets solved the same way. I would always make my ice chart as minus, minus, and plus here. And if the reaction happened to be going left, I would just get a negative X value. All right, and so the math would take care of it. Right, and so I never needed to know it. Right. On the other hand, it is there as a directional arrow, right? It tells me when compared to K, whether I need to go left, right, or do nothing to get to equilibrium, right? And so, you know, most of the semester has been about these three things, right? And they're two different things, right? Kinetics, again, is all about speed, right? I can't, in good conscience, say it's completely separate from thermodynamics. We talked a little bit about how delta H and the activation energy sort of, right, do determine which, what the relative speed of the forward and the reverse reactions are. However, they are mostly different, right? Whereas thermodynamics and equilibrium are all about establishing the balance between the products and reactants, no matter how long it takes, right? My equilibrium is my concentration balance. My thermodynamics is my thermodynamic balance, which relates mostly to energy, right? Entropy itself has some energy influence. After all, it's joules per kelvins, right? But if you look at what Q just told me, think about what delta G tells me, right? We've just been talking about how delta G is the way the universe decides what to do, right? And the big issue in what to do was a sign issue, right? If delta G is negative, that means what about the reaction? It's spontaneous, which means it happens without forcing it in the direction written, right? On the other hand, if delta G is positive, it means the reaction is not spontaneous. But if you think about it, if I flip the reaction around, the sign of delta G must change, right? If my products minus reactants gets flipped around, it's now reactants minus products. And so the way we normally interpret delta G as being greater than 0 is that the reaction is not spontaneous as written. But the corollary to that is that the delta G being positive must mean the reaction is spontaneous in the reverse direction. And as we were just talking about, if delta G equals 0, it's so hard to play this game with the chat. If delta G equals 0, I'm at equilibrium, right? In fact, delta G is actually telling me exactly what Q is telling me, right? If Q equals K, I'm at equilibrium. If delta G equals 0, I'm at equilibrium. Depending on the sign of delta G, I'm either spontaneous left or spontaneous right. Depending on whether Q is smaller or greater than K, I'm spontaneous left or spontaneous right. All right. And so the equilibrium constant and associated Q is really just telling me the same thing that delta G is telling me, because they are fundamentally the same thing, right? And the reason is because of my third standard condition. Right. Right. Technically, there is a distinction between being delta G and being delta G 0, right? The 0, technically not, it's usually described as, which is just, English for 0, right? The delta G naught is its standard conditions. The delta G would be the same value, but non-standard conditions, right? And that is mostly interpreted as temperature and pressure a lot of the times, but technically there are 3 standard conditions, right? Because quantity also matters. And so we talk a lot up till now about the temperature and pressure being standard, because especially when you're talking about energy terms, that's the big thing, right? But in general, that also requires that you have what is sometimes referred to as stoichiometric quantities of everything, right? Meaning 1 molar concentrations of solutions and 1 atmosphere pressures if your species are gases. And so technically, right, a delta G no naught would apply whenever your temperature or pressure are different, but also whenever you don't have the stoichiometric quantities of everything. Okay, and there is a correction to delta G naught for the concentration difference. And in fact, that correction is Q. Right. Specifically, right, if I have delta G at at standard conditions, right, and I want the delta G for a specific reaction mixture where the concentrations are not stoichiometric, I need this correction factor, which is RT, our usual old friends, R the gas constant, T the temperature in kelvins, and the natural log of Q. Right. In a very weird way, right? Delta G is the thing, right? We spent 6 weeks talking about K. K isn't even the second thing, right? K is an accident that comes out of the fact that Q is the second thing, right? Q is the correction for concentration to delta G, right? And the K just happens to fall out of the equilibrium condition, right? Which is that delta G equals 0, right? In some sense, what equilibrium really means is you're perched at a balance point between going left or right. Remember, my equilibrium is dynamic, so I do go both left and right simultaneously and equally so that nothing is really changing. You know, whether it's a phase change or a chemical reaction, that's what it means to be at equilibrium. There's no driving force for me favoring either direction, right? To go back to Owen's question, which I didn't mean to dismiss as I might have seemed like, but I don't want to get bogged down in it. That is the phase change issue. I am perched between phases. When I'm at 25 degrees C, I am not perched between being a gas and a liquid. If I'm water, I am a liquid. There is a driving force to be a liquid. If I take steam and put it in a 25-degree room, it wants to condense because the delta G is pointing in that direction, right? Equilibrium is the place where nobody's pointing in either direction, hands in your pockets, right? Even if you're at 298 kelvins and 1 atmosphere of pressure, because of the concentration issue, right, there is this value where you can reach equilibrium by adjusting the concentrations, right, so that there is no finger pointing in either direction. So delta G equals 0 is that point, which we call the equilibrium point, right? In some sense, that is simply a magic ratio of concentrations that perfectly cancels the standard delta G, right? If I want this to be 0, it's because this correction factor is equal and opposite to the actual standard Gibbs free energy. All right. And so that is, in fact, where K really comes from. It's not so much a thing, it's a correction factor to the thing, which is the delta G, right? Delta G is what's pointing a reaction in one direction or another, right? This equilibrium constant just happens to be the ratio of concentrations that eliminates the directionality and allows the system to sit at a position, right? And if I do that, right, I can actually calculate the K value from the delta G value, because in some sense, that's what it really represents, right? And so, again, because it's statistical, my delta G being 0 doesn't mean nothing's happening. It just means I've balanced the forwards and reverses. Kinetically, the rates are the same. Again, I don't know what they are or care. A really slow reaction sitting at equilibrium still has a really slow forward rate, balancing a really slow reverse rate. A fast reaction at equilibrium has a really fast reverse rate, balancing a really fast forward rate. All right. So I still know nothing about the speed of a reaction from the equilibrium position. All right. But if I, right, if I do the math, right, essentially what I have is a balance in delta G's of the forward and the reverses both being 0, right? Because thermodynamically, the delta G forward and the delta G reverse end up being the same and 0. Right, as the only number that actually will solve those two equations, right? But in terms of K, this gives me the rather interesting and powerful result that if I let delta G equal 0, which defines my equilibrium, right, then delta G0, which is my standard Gibbs free energies from the table in the back of the book, is minus RT log K. And of course, R is R, it's the gas constant, I know it. And T is whatever temperature I'm at, right? Again, with the usual caveat, right? T doesn't have to be 298, right? But if it's not 298, this is approximate, of course. I can make it slightly less approximate if I calculate the delta G not from the table of delta G's, but from the delta H's and delta S's. But again, in all cases, if I'm not at 298 kelvins, my thermodynamic tables aren't perfect. On the other hand, you might have noticed, or might not have, I think I said it, but might not have, right? All of my tables of equilibrium constants were also at standard temperature and pressure. Right. I don't know offhand what the Ka is for boiling acetic acid. Right, because my Ka, and like all equilibrium constants, it should be temperature dependent. My Ka value comes from the table of standard temperature and pressure K values. Right, and if I really need the Ka of acetic acid in boiling water, right, I may have to measure it. On the other hand, I can now approximate it, right? Because I can calculate the K approximately at any temperature I want using the delta G values. Right. And so from this moment forward, God help us all, I don't really need to give you the K values. You don't even need to have a table of K values. What you do need to have is a table of thermodynamic values, because I can use those to find the K value either exactly at 298 Kelvin or approximately at other temperatures, right? Because again, K is really just a magic ratio that makes delta G 0. And so here's a random reaction. It's not a Ka, it's not a Kb, it's not a KSP. This reaction is not in a table in the back of the book anywhere. Its equilibrium constant may be on the internet. I haven't even looked. Right. On the other hand, if I have my thermodynamic tables, right, since the two reactants in the product are all relatively common species, they are in my thermodynamic tables. And so I can actually calculate the K, again, either exactly if I'm at 298 Kelvin, which I'm not, or at least approximately at non-standard temperatures using the delta G values. And so again, since I'm not at 298 Kelvin, I'm going to calculate the delta G. I sometimes like to call this pseudo naught, right? Because I'm calculating what looks like a delta G 0, because I'm using delta H naught and delta S naught, right? But I'm doing it at non-standard temperature, and so it's not quite a standard delta G, right? And so again, if I go to my table of now thermodynamic variables, right, I can calculate the delta H for the reaction from the products and the reactants and their delta H's of formation, right? Since hydrogen, of course, still an element, its delta H of formation is 0. Carbon monoxide is minus 110.5. And methanol, which is what CH3OH is minus 201.0. And so the delta H standard for this reaction is negative 90.5 kilojoules. Right. If we care, and I don't necessarily in this context, right, it's exothermic, so it's enthalpically favorable. Right. Unsurprisingly, the entropy change is entropically unfavorable, right? Because of course, again, you know, just qualitatively, I'm going from a mixture to a pure substance. I've got 3 moles of stuff becoming 1 mole of stuff, right? So everything's pointing to entropy decreasing in that reaction. And so it's no surprise that my delta S ended up being negative. All right. Those numbers, again, are exact at 298 Kelvin. I'm assuming that they are temperature independent in doing what I'm doing next, even though I know they are not strictly temperature independent, which is why at this point, this becomes an approximation to the actual delta G value, since I do not have thermodynamic tables at 250 degrees Celsius, right? And so my delta G pseudo naught, because again, it's really no longer standard, as soon as I stick that 250 degrees C in there, right? Again, when I'm combining delta H and delta S, be careful about units, right? The tables are in joules for entropy and kilojoules for enthalpy. If I'm going to add them together, I need them to either both be joules or both be kilojoules. In this case, it makes sense to make them both joules because, of course, they also have to balance the units of R if I'm going to get proper cancellation of units. If you still haven't mastered units, I still encourage you to do so, unless you've recently changed your major to business, And even then you might care, right? Maybe psychology, you don't care. I don't know. Even in business, it's going to matter whether you get paid in dollars, euros, or rupees. So units matter, but if you're not doing a lot of algebra, maybe you don't care as much. But if you're doing any kind of algebra, so if you're in any kind of scientific discipline, right, the unit cancellation is always an issue and frankly always helpful in terms of determining what you need for constants. Thanks to the internet and largely my asynchronous audience, I have never had so many students calculating things in Pascals before, which both makes me smile and cry. Anyway, so on the left, I've got 24,174.5. Somehow, after all that unit talk, I lost the joules. All right. And on the right-hand side, I've got joules, so they all cancel nicely. Get everything on the left-hand side except K. And of course, the anti-natural log is e to the x. And I get a value for K, almost magically, from delta G. Again, right, I expect this to be approximate because of the temperature. But I would expect it to be exact at 298 Kelvin. So at the very least, this is equivalent to my KAs and KBs and KSPs and all the tables I have in the back of the book, because it does give me exactly the equilibrium constant at standard temperature and pressure. Right. And not to belabor the point, but it's worth saying again, if I'm at any other temperature, right, if there's nobody else has measured it, the only way to get the exact number is going to be to measure it myself, which sometimes happens. All right. Yes, no, maybe. All right. And so, I mean, there's two, again, morals to that story. One, I don't need tables of equilibrium constants as long as I have thermodynamics. All right. And two, the bigger story here really is that delta G is the thing. All right. Equilibrium constants are really just a proxy for delta G. Right. It happens to be the ratio that balances the delta G zero, right, for the reaction. Starting possibly Monday, we'll talk about redox reactions. For redox reactions, it's actually more common to talk about cell potential, which, as you'll see, is another proxy for delta G. Right. Delta G really is the thing. A lot of the other things like K or E cells, some of you stumbled across E cells for your projects, right, are really just proxies for the thermodynamics. And if I could take a slight detour here, right, that's why, you know, I framed the question for Project Through the way I did. It's really a thermodynamic issue, right? But whether you're going to end up talking about equilibrium constants or delta G's, or if you've got redox reactions, right, cell potentials, right, really just depends on the discipline specifics. In the end, they're all really thermodynamics. K is just delta G in a slightly different form. And as you'll see next week, cell potential is really just delta G in a slightly different form. Right. if we want to do the same thing, and why not, for my favorite reaction, and there's a reason I do this. Many of you have actually been doing this reaction, you know, all you hydrogen fuel cell people, right? Right, so I forget it, right? If I do it at standard temperature and pressure, right, I should get the exact number because, of course, my delta G tables are good. I shouldn't really say exact because, of course, those are actually measured numbers also. So they should at least be accurate to the number of digits reported, but they're not exactly exact, right? But this should give me, therefore, right, an actual accurate K value because I'm at standard temperature and pressure, right? And so this is actually a formation reaction. I've got standard elemental forms of hydrogen and oxygen turning into water, specifically steam. And so if I calculate the delta G naught, it's minus 457.2 kilojoules per mole. Very negative, right? That is a relatively large negative number, so it is spontaneous. And, you know, in a somewhat nonsensical say, I'll say it anyway, it's very spontaneous, right? That is, you know, a bold-faced finger pointing in the forward direction. And so unsurprisingly, if I go through and then calculate the corresponding equilibrium constant, I get a gigantic value, right? This is bigger than super freaking big, right? This is SDFB, or it could be SFB also if S stands for supercalifragilistic, XBL, big, right? It's 10 to the 80th. Right. And so in a very real sense, that reaction essentially is unidirectional. Right. It is not really an equilibrium reaction.
I have a question about this.
Yes,
So,
sir.
like, in like an experiment, like would there essentially be like in a practical application, there would be absolutely none of the reactants left over? Like, it wouldn't be just like a really small, like really, really like infinitesimally small amount of reactants left. Like, it would be basically
if
zero.
I'm doing this reaction,
Yes.
yeah, I mean, if the question on the chat is, if I'm doing this reaction, would the amount of hydrogen or oxygen actually be zero? Technically, no. Right? You know, I mean, practically speaking, it is probably not measurable, right? But it technically, you know, there's technically still an equilibrium there, right? But it, you know, in some sense, it's meaningless, right? It's meaningless at much smaller numbers, frankly, right? I mean, if you think in terms of moles, 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 right? If I have a mole of something that's 10 to the 23rd atoms or molecules, right? If I had one molecule of something, right, that's 1 part in 10 to the 23rd, right? So, you know, forget 10 to the 80th. At the point at which I'm at 10 to the 23rd, I'm looking for a single particle in a beaker of water, right? I mean, it's just not able to be found, even at slightly smaller numbers. It's not until I maybe at, you know, I don't know, 10 to the maybe 17th or so that I might have a hope of detecting it. So, you know, the short answer to your question is, yeah, I mean, it's functionally zero because you're not going to be able to find it. It's so small, right? On the other hand, is it in fact actually zero? It should not be, right? Because again, technically that reverse process could still happen, although it kind of depends on whether you're containing your water vapor or not, right? If you let your water vapor waft away, it will be actually zero at some point, but I mean, technically there's still an equilibrium there because the reverse reaction can still generally happen. But for all intents and purposes, yeah, you're not gonna find any of the limiting reactant left by any normal means. Yes, no, maybe. Just for yucks, right? If I do the same calculation, I really approximated this. In theory, I should go back and calculate the delta G from delta H and delta S. But this is another case where the equilibrium constant is actually shrinking as the temperature goes up. Right. And so, you know, in terms of, I don't know how this is maybe too specialized, but so, you know, in terms of some of my reactions that I can do, I mean, when there's optimum ranges for doing reactions, it's largely because of that. My equilibrium constants, right, can be going up or down depending on the relative delta G's or the relative delta H's and delta S's, right? They could be going either way. Typically, there's an optimum range where the equilibrium constant is suitable, right, to give me the, I'll go with maximum amount of product. And hotter is not always better. Sometimes colder is better in terms of overall yield, although hotter is always better for rate, right? And so one of the goals of the project ultimately is to talk both kinetics and thermodynamics, right? And so, you know, in a real reaction, there's a balance, right? Maybe your reaction is thermodynamically best, you know, at 10 degrees Kelvin. On the other hand, if it's so friggin' slow that you'll be dead before it's over, there's really no point in maximizing the yield by minimizing the rate, right? And so you do kind of have to look at both of them separately, but at some point from a practical standpoint, right, there's a balance. For biological systems, since there's a lot of you who have biological topics, right, typically your enzymes, right, have optimal rates in the vicinity of body temperature, or for cold-blooded creatures, normal ambient temperature. Right. Yes, the farther away from 298 kelvins you are, the less accurate you're going to be if there's any temperature dependence whatsoever. Right. Yes, no. I will send an email this weekend, again, mostly apprising you of some of the language differences. It's a little hard because there's so many different categories. But again, I mean, you know, if you keep typing in Arrhenius or activation energy for a biological system where they don't talk about it, they talk about Vmax or one of the Michaelis-Menten parameters, then you keep finding nothing. And so part of the issue with any of those topics is learning enough of the lingo for the discipline to be able to do an appropriate search, right? And so fortunately, for thermodynamics, those search terms are a little less varied than they are when it comes to talking about kinetics of reactions, especially because for reactions like this, right, you know, we're back to limiting reagent type reactions. And so since they're mostly unidirectional, they get talked about in a much more limited way than things that have robust equilibria. in robust, not so much robust, but fun kinetic issues. Although for most of the people who said I can't find anything kinetically, I could find it. So a lot of it is really just, again, the language of the search. And so I will try to give you some more context for that, but I will do that in an email, since between the 5 people in the room and the 32 people on the Zoom, we are missing 7/8 of the class. So other questions or problems?